All right, let's talk about something that trips up almost everyone in data science. It's this weird thing I'm calling the prediction paradox, and it's all about the massive gap between explaining the past and actually predicting the future. So, have you ever seen this happen? You get a model, and it looks perfect. It can explain every little twist and turn in the data you already have. But the second you ask it to predict what's coming next, it just completely falls on its face. It's a super common, super frustrating problem, and we're going to figure out exactly why it happens. And look, this isn't just some random fluke. It's a real, recognized issue, and it even has a name that perfectly captures the problem: the prediction paradox. To really get this, you have to understand that explanation and prediction are playing two totally different games. Explanation, that's all about looking in the rearview mirror. It's about finding the story, the causal links, in data you've already collected. Prediction, though, is all about looking forward, through the windshield. It's about forecasting what's going to happen with new data that the model has never, ever seen before. And this isn't just my opinion. Researchers have been talking about this for a while. You see it right here in this quote from the European Journal of Marketing. Just because a model fits your old data like a glove doesn't mean it won't completely fall apart when you use it out in the wild. You know, a great story about what happened yesterday doesn't always make for a useful map of tomorrow. So a huge part of the problem comes down to the report card we use. We often rely on a score called R². Think of it like this. A model is like a student who's been studying for a test. A high R² means they've perfectly memorized the study guide, but that doesn't tell you if they can handle a pop quiz with brand new questions. When a model gets too good at explaining the past, it's usually because it's overfit the data. It's memorized all the noise and quirks instead of learning the actual underlying lesson. Okay, so if our old report card is misleading us, how can we actually test a model's true predictive chops before we bet the farm on it? Well, lucky for us, there's a tool designed for exactly this, and it's called PLSpredict. So what is PLSpredict? At its core, it's basically a stress test for your model. The whole idea is to build your model on one pile of data, we'll call that the training sample, and then you force it to make predictions on a completely separate holdout pile that it's never seen before. This is the ultimate test of whether it can survive in the real world. So how exactly does this whole holdout test work? Let's pop the hood and take a look at this really clever process called cross-validation. The idea here is actually pretty simple and elegant. Imagine your data set is a pizza. First, you cut it into, say, 10 equal slices, or folds. Then, you take one of those slices and you set it aside. That's your holdout. Now you train your model using the other 9 slices. Once it's learned everything it can, you bring back that one hidden slice and say, okay, model, what do you think is on this slice you've never seen? And you just repeat that process until every single slice has had a turn being the final exam. And this right here is a perfect picture of that in action. You can see how each chunk of the data gets its turn to be the test subject. This makes sure that every single data point is used for both teaching the model and testing it. There's just nowhere to hide for a model that can't handle new information. It's a really robust system. Okay, so we've put our model through the ringer, we've tested it, now what? How do we actually grade its performance? How do we know if its predictions are any good at all? Well, we judge it in a few steps. First, we measure how far off its predictions were from what actually happened. We use these error metrics, and you can just think of it like a golf score. The lower your score, the better you did. But a low score compared to what? That brings us to step 2. We have to compare our model's score against a really, really simple benchmark. Like if we're predicting sales, the benchmark might just be guessing last year's average sales for every single day. And if our super fancy complex model can't even beat that dumb simple guess, well then it's pretty much useless. Now, I know this flowchart might look a little intimidating at first glance, but it's basically the official scorecard that researchers use. They start at the top and they just follow the arrows down. And all along the way, they're comparing the model's performance to those simple benchmarks we were just talking about. This whole process leads them to a final objective grade. Does the model have low, medium, or high predictive power? It's a really thorough way to make sure the results are solid and not just wishful thinking. Theory is one thing, but let's see how this all shakes out in a real-world scenario. It's time for a head-to-head showdown between some competing models. This example comes from a study where researchers were trying to figure out what makes people click buy on travel websites. So they built 3 different models, some simple, some more complex, to try and explain a person's intention to make a purchase. But remember, the big question wasn't which model told the best story about past purchases, but which one could actually predict who was going to buy in the future. And the results are in. Check this out. The original model had a pretty decent prediction error, but when they tried to make it more complex, the error actually got worse. The predictions were less accurate. But the big surprise was Model 2, the simpler one. It absolutely crushed the others with a much, much lower error score. This is the prediction paradox in action, right here on the screen. So, the winner, by a landslide, was the simplest model. It made the most accurate predictions, proving once and for all that more complex is definitely not always better. This is such a classic case where adding all the extra bells and whistles just made the model worse at its actual job, probably because it got too distracted by the noise in the training data. So after all that, why should you care? What's the big takeaway from this whole prediction paradox thing? Well, at the end of the day, this is all about making sure our theories and models are actually useful. It's about building a bridge between a cool idea on a whiteboard and a tool that can actually help us make better decisions out in the messy real world. We need models that aren't just good at telling us stories about what already happened, but are also reliable guides for what might happen next. And that really leaves us with one final thought. The next time you come across a model that claims to have all the answers, I want you to ask yourself a question. Will you ask how well it explains the past? Or will you ask the much more important question, how well does it actually predict the future?